In this video, we are going to interpret the outputs of a multiple linear regression analysis in STATA. At this point, we've followed all the procedures from testing assumptions, choosing variables, assessed interaction, and we've also assessed for confounding. Therefore, we have got now a final model that is ready for interpretation. We have previous videos that have covered procedures 1 up to 4. You may consider watching them to understand how they are done in STATA. Here is our hypothetical dataset that we want to use for interpretation of multiple linear regression analysis in STATA. We have our outcome variable, which is systolic blood pressure, and we have got 5 independent variables, 3 which are numeric, and then 2 which are binary categorical variables. So we are assessing for factors associated with the systolic blood pressure, our outcome. To run a multiple linear regression analysis in STATA, simply go to Statistics, Linear Models and Related, then click on Linear Regression. In this dialog box, we specify the dependent variable, which is systolic blood pressure. Then we put in our numerical variables. We have age, we have BMI, and exercise. But for the categorical variables, we shall use the 3 dots to show STATA that this is a factor variable and it is gender. We add it to the variable list. You will see that it is added but with an I dot before the variable name to show that it is a categorical variable. We do the same for smoking status, which is also categorical, and then we add it to the variable list. We click OK. It could also be as simple as putting the variable names and then typing their I dot. Then we click OK. In this output, we have a table showing the source of variations, that from the model and the residual. We have the sum of squares. We have here the degrees of freedom. For the model, we have a total of 6 variables, which is n minus 1. Then to give us 5. Then we have for the residuals, we have a total of 120 observations minus a total of 6 variables to give us 114. Overall, it is also 120 minus 1, that's n minus 1, to give us the overall degrees of freedom. We also have the mean sum of squares given here, which is just a ratio of sum of squares to degrees of freedom to get this mean sum of squares. We've already seen here number of observations, 120 in our data set, and we have the F statistic, which is simply a ratio of the mean sum of squares from the model over the mean sum of squares from the residuals to give you that F statistic. Then we have here the p-value for the F statistic, which is statistically significant. It is less than 0.05. Whereas you're seeing here 4 zeros, there is no such a value of p-value of 0, but it is because of the rounding off to the 4 decimal points. But usually when we are reporting this in our analysis, we just say p less than 0.001, even if your p-value was set at 0.05. So that's the overall p-value for the model, which is testing that the null hypothesis that the overall R squared in the population is equal to 0, whereas the alternative is saying the overall R squared in the population is not equal to 0. We have here R squared value, which shows us the percentage of the variation in our outcome variable systolic blood pressure that can be explained by the variables we've put in the model. This value of 0.7203 shows us that the predictors we've put in the model account for 72.03% of the variation in systolic blood pressure. So the higher the value, the better the model that will fit. We have an adjusted R squared, which is more of a computational adjustment of the R squared in the population to avoid overfitting of your model. Below down here, we have a table of coefficients. we have our outcome variable on top, and then our independent variables down here. We have a column for coefficients that have been calculated for each independent variable. We have the standard errors, and then the t-statistic, which is basically a ratio between the coefficient and the standard error. We also have the p-value corresponding to that t-value of t, and then the 95% confidence interval for the coefficients. Among our independent variables, we can see that our first three variables are numeric. Then we have these two variables, gender and smoking status, that are categorical. When interpreting the coefficients for the numeric variable, this coefficient here is simply an expected change in the systolic blood pressure for every unit increase in age, keeping all the other factors constant, and when there is no interaction between age and other factors. There are three concepts as we are interpreting. Yes, this is the expected change in our outcome for a unit increase in age. However, we have two additional conditions that we have to specify. That is, when age is not interacting with any of the variables in the model, meaning you should have checked for interaction in your model and ensured that there is no interaction in the model. And secondly, when all the other variables are kept constant. A similar interpretation, for example, for BMI also, 1.485 is the expected change in the systolic blood pressure for every unit increase in BMI when keeping all the other factors constant and there is no interaction between BMI and the rest of the independent variables. If the value is a positive, so you would specifically say this is the expected increase in systolic blood pressure for every unit increase in BMI, keeping other factors constant and when there is no interaction between that variable BMI and the rest of the variables. Now, when it comes to a variable like gender, remember gender, it was male and female. If you look at the coding, females are coded 0 and then the males are coded 1 here. So when we have the males coded 1, they are being compared to the females coded 0. So this is the expected change in the systolic blood pressure when males are compared to females and the difference in coding is unit, keeping all the other factors constant and there is no interaction between gender and other variables. For the categorical variable, we are also calling this a change in our systolic blood pressure, but for this category males compared to females. There is an extra condition of when the difference in codes is unit. We have a 0 to 1. Not one variable is coded 0 and maybe another one is coded 4. We are talking about when the difference in the way they are coded is unit. Then we also include the condition of other variables constant and when there is no interaction. If it is positive, it also means an increase in our outcome, systolic blood pressure. A similar interpretation for smoking status. This is the expected change in the systolic blood pressure when smokers are compared to non-smokers, when the difference in the coding is unit and there is no interaction between smoking and other variables while keeping other variables constant. A negative is indicating that that change is a decrease. So the value of the constant here tells us that this is the value of the outcome when all the other variables in the model are set to 0. Another important part for us to look at is the p-value. A p-value less than 0.05 indicates a statistically significant variable. All the variables except smoking are statistically significant. It is only smoking that is non-significant. It is a non-significant predictor of our systolic blood pressure. We also have the population 95% confidence intervals. For us to interpret or make sense out of them, we have to consider the null hypothesis. The null hypothesis this p-value is testing is that the coefficient for that variable in the population is equal to 0. So if your confidence interval contains a 0, if you were to draw a number line and you put the minimum value and the maximum value, if 0 falls within the range, then that's not statistically significant. For example, when you check our smoking status here, it runs from -3 to +2. 0 is included within that interval. So that variable is not statistically significant. Whereas the rest of the variables, this is 4 to 10, 0 is nowhere within that interval. One other thing we can look at when interpreting this output are requesting for standardized coefficients. By going through statistics, linear models and related, then linear regression. Under reporting, we ask for standardized beta coefficients, then we click OK. While these unstandardized coefficients depend on the unit of measurements, we have the standardized coefficients beta that shows us the rank for us the variables in terms of their relevance to the model. So you see that age here is having the highest value 0.7, followed by 0.3, that's BMI. We have 0.2, that is for gender. It shows you the order in which they are relevant to our model. So age is the most relevant, followed by BMI, and then gender. If you found this video useful, consider liking and subscribing to the channel so that you don't miss out any of our episodes. In our next episode, we shall be looking at how do we interpret a model if we had interaction terms in it. See you in the next episode.